Good afternoon. I'm Dan Freed. It's a pleasure to welcome you to this third in the series of 7 lectures on the Millennium Prize problems. It's a series of lectures sponsored by the Harvard Mathematics Department, the Harvard Center of Mathematical Sciences and Applications, and the Clay Mathematics Institute. You can find the previous lectures on the CMSA, the Harvard Center YouTube channel, and this lecture will also appear there in about a week. So there's a lot I could say about our speaker today, but I think it's best if he says it himself. So we're delighted to have Pierre Deligne from the Institute for Advanced Study telling us what is the Hodge conjecture.
Thank you. So the Hodge conjecture tries to characterize the circle, the cohomology class of algebraic circles on projective singular, non-singular algebraic variety over the complex number. So the first thing I want to do is try to give picture for all the words I just used. So first projective. First projective space. I start with projective line. So I could not go far enough, and to get the projective line to the line, you had one point at infinity. So I want to explain why. So in analysis, often one had one point in one direction and one point in the other direction. Here I want only one point for both directions, and the reason is as follows. Suppose you have some origin here, and you look at a line through the origin. Then for each position of the line, you hit a point on the line, except when it is parallel, and then you will hit this point at infinity. And you see, the reason you have only one point at infinity, you have only one parallel line, and if you move like this, you go to infinity and you come back from the other direction. So a neighborhood of infinity is like a neighborhood of any other point. And also one can understand in this way projective coordinates. So if I have a coordinate system, I have the origin here. So to give a line through the origin, it suffices that I give some point, and then I have this line, and 2 points which are with proportional coordinates will give me the same line. So in this way, you have projective coordinates for a point of projective line, which is a pair of points of number xy, not both 0, which will define a line, which will define the point. The rule being that x double dot 0 is the same as a multiple of it. And yes, I should tell another way of thinking to this. So you have seen that the whole projective line is like a circle, and I want to see another way of this fact that if you go to infinity, you come back from the other direction. If you consider the function y equals 1 over x, you see just the same phenomenon. If x becomes closer and closer to 0, you get something bigger and bigger, at 0, and then you come back from the other direction like this. So this is projective line. Now I want to tell projective plane, and then I will have projective space. So for the projective plane, you look at the plane of the blackboard, and then one add 1 point for each direction meaning a system of parallel lines. And all those points which you get from the line at infinity, and again, if you have a direction going far in this direction is the same as going far in the opposite direction. It's the line which counts. And again, you can have projective coordinates. Oh, this I did not need to erase. So I have coordinates in the ordinary plane. I have the origin here. This is the z-axis. And now again, for each position of this line, I have a point of projective plane. And if it is parallel, I get one of the points at infinity. And so again, you see that if I give x, y, z some point, I get a point of projective line. X, y, z is up to a constant. And that's projective coordinate on projective plane. So triple of points x, y, z up to multiplication by a number. And now, if you want projective space, in each direction, you will add a point. It will be plane at infinity. And you have projective coordinate like this. So that's for projective space. And you see it can be expressed rather algebraically. One remark is that if you want to describe some curve or some variety using equation, you should add a polynomial equation. But this polynomial should be homogeneous, so that it vanishes here if and only if it vanishes at some multiple. So to define curves of variety on projective space, you use homogeneous polynomials if you want algebraic varieties. So far I have been using real number, and it costs nothing, and it gets more interesting if you use complex numbers. So the usual rule of the game is you make the picture into real space or real projective space, and you don't forget when needed that in fact you are speaking of the complex projective space where some things are simpler in fact. So let me give an example of how things become more simple. If you take, for instance, the cubic curve, this one, or then if you look at the real locus, the real solution, the shapes are very different. From one, you will have something like this, and for the other, you will have something like this. So you see that, of course, I should write it homogeneously. So then it's I have added a point of infinity to what I have drawn. So it shows that it can be difficult just from not knowing the degree or basic property of the equation to tell what kind of shape you will have. And if I look with some number here, there will be a transition in between the two where I get something like this. Before I have this, one has a transition like that. Now, in the complex story, you don't have this kind of problem. The basic shape of the set of solutions will be the same, and it will be a torus in both cases. The reason for that, here what happened is you had some parameter you were putting, and there were some singular value for this parameter, where you got this singular point. Yes, I make a wrong picture for lambda equals 0. I have a cusp. Now, in the complex domain, again, there will be some singular value for lambda, the same value, 0. But now you have the whole set of complex numbers, which is a plane, and you can go around this point. And then you see that the topology will not change. So, for instance, if you take an hypersurface of some degree with no singularity, the topology will not depend on the actual coefficients you have. But what happens, it can be very interesting to understand what happens when you turn around a singular point. So instead of a jump, you have what one calls the monodromy there. Now, I still find it quite miraculous that just writing some equation in the complex situation, one can obtain very nice varieties of spaces which could be difficult to picture otherwise. And also, what is as surprising is that having the equation can be used to understand the shape of those spaces. So, as an example, in the real case, in a projective plane, if you take a curve defined by one equation, the topology is rather boring. You will have just a bunch of circles. Here, what can be complicated is that some circle can be inside another. But like in the case of cubic, you had the example. In one case, you had just one circle, and you had topologically two circles. Now, in the complex situation, if you look at complex plane curve, if you take a line, then what you get is simply a two-sphere. The picture is that you have the complex number forming a plane. You add one point at infinity, but just one point for all of it. And then what you get is a sphere, because it's obtained by gluing the unit disk with the complement of the unit disk, which is the same by the transformation z to 1 over z. And so you have two disks which you glue along their boundary, and this gives you a sphere. For conics, it's the same, so degree 2 equation. And the reason is that if you have a conic and you take a point on it, you can use it to project on a line. And this gives you a one-to-one correspondence. This point gives this point, and you have the tangent, which also gives a point. So, and as I have already said, if you have a cubic plane curve, you get something like a torus. And in general, for a curve of degree d, you get something like a torus with a number of holes, the number of holes being d minus 1, d minus 2 over 2. Yes, I would like to give another example that it's miraculous that our just equation can be used to construct interesting shapes. Here we had only variety of even real dimension, but you can also get interesting thing in odd dimension. If you take a singularity like the one given by x squared plus y squared plus, I hope I will have the correct number. So I want to have, we have to check how many. And yes, this is in the ordinary in C at some power. That's the little dots. I don't remember how many. So you have a singularity. Now you can cut it with a small sphere and the real sphere, and the intersection will be something interesting of odd dimension. And for instance, for this one, if you take the correct number of variables, you obtain something which is the seventh sphere topologically, but not as a differentiable manifold. So, and the equation can be used to find invariant, which give you what it is. So that's what I want to tell, the picture I wanted to give about complex projective non-singular algebraic varieties. Now I need to explain something about homology and cohomology. Again, I will try to give pictures. So you have some variety like this plane. No, I am not especially complex for the time being. A zero circle is just a sum of points with some integral coefficients. Now, a one circle will look like a bunch of circles, but usually it can be more complicated. And no boundary, so I don't want to have something like this. So one circle are one-dimensional, oriented, you can integrate things over them, and no boundary. Two circles are something two-dimensional if you are in tree space, and again with no boundary. And you have also chains. For instance, this will be a chain, and it will have a boundary, which is a zero circle. Here, what I have drawn is the boundary of two chains. And because it's a boundary, itself has no boundary. So this is an approximate picture, but you see those things, you have to look at circles and consider two circles are equivalent if they are the boundary, or that a circle is equivalent to zero if it is the boundary of something. For instance, in tree space, if you have two circles like this, yes, that's too easy. You can either fill it like this, or you could fill with a cylinder between the two. So you have homology equals circles modulo this equivalence. And in 3 space or 2 space, it's not very interesting. For 0 circle, you have that the class of the 0 circle depends only on the sum of the ni, and all the rest is 0. Every 1 circle is the boundary of something, every 2 circle is the boundary of something. But if you look at more interesting shape, then that's not the case. So suppose you look at a torus. Then if you look at this circle, it's not the boundary of anything. Or if you, the same if you look at this circle. And in fact, any circle up to this equivalence is a linear combination of those two, n times the one times the other times a multiple of the other. And I would like to give a picture explaining this. To see this, I like to think of the torus as follows. You take first a cylinder. Now, it's difficult with paper. You think rather it's a garden hose, cut, and then you glue this like this. Now, a convenient picture for this is that you view it as a square, but you identify those two sides, that's to make the cylinder, and afterward you identify those two. So what I have written here, on the one hand I will have this circle, which is something close because this is the same point as this one. The other one is this circle. And now let us consider something else. I will make one turn around, but in the same time, I will make a turn in the other direction. So this will give me this. And this is another example of natural circle. And at least in this example, you see that this one is the homologous to the sum of those two. So that's homology. Yes, and I would say that the reason I start speaking of homology is that if you have an algebraic circle, something defined by equation in complex projective space, it gives you a circle, always of even dimension. And we will want to understand what the class of that circle are. Now I need to speak of cohomology. Now, you are somewhat familiar with it if you know something about electromagnetism or about fluid mechanics, because it appears somewhat in disguise. So then you are familiar with the following. You have functions in, say, in 3 space. You have vector field, again vector field, and again functions. And you have natural map to a function. You can associate its gradient, to a vector field you attach is rotational, and to a vector field you can attach its divergence. And a basic property is that the composite of two such maps is zero. Now, and so we can do again what we did with circles. We can look for objects which map to zero by taking two equivalent if there are differences in the image of the previous one. So those are the cohomology group. And as it was the case for homology, nothing interesting happens in Rn. You have that the only functions whose gradient is trivial, it's the constant function. And so that's the first cohomology group. But for the rest, if a vector field has zero rotational, it's a gradient. If a vector field has zero divergence, it's a rotational. And any function is a divergence. So you have that all auto hi are zero, the same thing that we had for homology in R3. And the same way that if you don't work in this space R3, but in a more interesting space, you can redo things now. This is a bad way to look at this complex because I have used the metric to be able to write like this, but on any manifold one can do something similar. And let me tell, and one will have a sequence of space from index by 0 to n when n is the dimension. So let me give the simplest case where I consider simply a circle. Then I have functions which I view as function of an angle, and I can map them to their derivative, which are again function of an angle. Now, as before, a function whose derivative is 0 will be a constant function, so the 0 cohomology group will be the constant. But this is more interesting. If you take a derivative of a function on the circle, its integral will have to be 0, because the integral tells you vary from one point to another, but if you go all around, you did not vary at all. So in this case, you will have for the circle, H0 is R, say, and H1 is R also. And you see that it is this circle which is responsible for the existence of this homology. And so in general, you have the same story, that the obstruction for which those groups corresponds exactly to the circle modulo homology you can write. Okay. So sometimes I will be a little vague between homology and cohomology, because in addition there is some duality, which you see here, functions here and here, vector fields here and there. And so, in fact, there is a natural isomorphism between homology and cohomology, and I will be vague when I use one or the other. Now, another thing which one sees here, so if one look at a complex variety, like something defined by equation in a projective space, and I assume non-singular, so near a point, if you look with a microscope, it just looks like Cn for some n. And in particular, if you look at the tangent space of a point X is a C vector space. In the same way that for an ordinary variety, a tangent space is a R vector space. If you are in the complex situation, tangent space are complex vector space. And what I will care about is that this gives some symmetry. If you have a C vector space and a vector, you can multiply it by a complex number of absolute value 1. So you can make this kind of rotation. You have in the complex number, you have the unit circle. And if you're in a complex vector space, you can multiply a vector by a complex number of. So you have this circle action. And as you see here, this Durham complex is based essentially on vectors and things you can do with it. So it's not surprising that you have this action of the circle also on each pieces of this Durham complex. You have to look at the exact definition and a better definition than this for the Durham complex. Now, those maps are not at all compatible with this action of the circle, but one of the beautiful discoveries of Hodge is that despite this fact, this symmetry you have by the action of the circle pass to the cohomology. So you look at some cohomology class, it will be possible to represent it by something so that if you move it by the circle, it remains with zero differential. Then we have this gives the way of how to multiply this cohomology class by a complex number, to have the circle acting on the cohomology. So that's the basic fact of Hodge theory, that if you look at the cohomology of complex algebraic variety, on it you have a circle action coming from the action of the circle on each tangent space. And now I can state the Hodge conjecture as Hodge stated, that if you have an algebraic circle, on the one hand you have something integral, integral homology or cohomology class, I will not make the difference. And also it will be fixed by this action of the circle. That's what means by type PP. And the conjecture is that this is the conjecture of Hodge was that this was characterizing the class of algebraic circles. Now, what are the difficulties? First, it's wrong. And this was found by Attia and Hirsebroek, that yes, and also one thing I should say, when I say algebraic circle, one has things defined by equation, but they have to be taken with a multiplicity which can be positive or negative. So we have a difference of concrete algebraic objects. Now, all the counterexample we have, it remains true that a multiple will be given by an algebraic circle. So if in those coefficients I allow rational number, then Hodge conjecture remains possible, and that's the usual notion of Hodge conjecture, but it was not what Hodge was telling. Now, another difficulty is that we would like to have more precise conjecture. For instance, we would like to know which multiple is needed so that one can hope it to become algebraic. And there are recent examples that you can have a family of variety, some circle which is Hodge all along if you deform it with the family, but you need a different multiple for it to be algebraic. So it's not a topological question to know which multiple is needed. Another problem is that we don't know at all when you can have a multiple of something positive, an actual circle, and not something which is positive and negative. And this makes a lot of methods to construct objects inapplicable, because if you wanted to have an analytic construction, usually you want to have the minimum of something and hope for the best. But if you have an object which is both plus and minus, it's not clear how you can do anything. So those are some first difficulty. Now, I would like to show why it is so difficult to either prove or disprove the Hodge conjecture. First, if you want to prove it, you have to construct algebraic circle. And there we really have very few methods for doing that. Naively, you think you have a variety defined by polynomial equals to 0 in projective space, and you add some more polynomial and you get something. What you get will be not interesting. It's well accounted for and you need much more. Now, if you try to do this algebraically, the only thing which can happen is that you take a few equations to define some circle, and this circle will be reducible, will split into two pieces. And then you can take one of the pieces, and this could be something interesting. But we have really no good way of knowing when you can hope that some complete intersection like this will decompose into pieces. Let me give one example of such decomposition, which is completely irrelevant for Hodge conjecture because it isn't a case where we know everything, but to tell how things happen. So I will be in P3, and I will consider yes, and no, I should not. Sorry. I will use projective coordinates, so I should write U4, T, U3, T2, 2. No, I need 3 only. So this for given T and U defines a bond in projective tree space. So this is a curve in projective tree space. And it's easy to find some quadric on which this curve lies, because if you take the product of those two numbers, it's the same as the product of those two. And I let you find two other quadric which give this. Now, if you take two of those quadric, what you will get is a line plus the curve I am considering. So this is an example of where things decompose. What happens is that you have two quadrics which have a line in common. So the intersection contains this line and something else, which is a curve like this. So here one sees how things can decompose, but to predict when this will happen and to relate it to the property we want for Hodge, we have no idea. Now, I want to explain another difficulty, is that it's rather unnatural to consider only the class in cohomology, this class invariant by the circle. Because if you consider an actual algebraic circle, there is a much more precise invariant which one can consider. So I told you that a cubic curve is a torus. This torus has a natural group law. And so if one has a collection of points, a zero circle, one can take their sum, and one has an invariant which is a point of the torus. And so that's a continuous invariant attached to a circle. And in general, if you have a circle Z of codimension D, you will have this invariant I was telling in H2D, but in addition, you have not, if this first invariant is 0, you have a second invariant in the real cohomology in the preceding group modulo the integral. So something like a product of circles. And in an extension of the Hodge group by this continuous group, that's where it's natural to look at what the class of a circle is. Now, why does it matter? A basic method for trying to understand algebraic variety is to cut them in slices like a salami. So you have some algebraic variety. If I were in a affine space, I would say I cut them with parallel upper plane. And so those sections have one smaller, one less complex dimension, and many things can be done by trying to reconstruct the property of the variety in terms of this collection of slices. Now, a case which happens in some, oh yes, I would say that the basic difficulty here is that one has this Hodge conjecture here to tell which class is algebraic. But if we look at the extension group, which is the natural receptacle for a class, we have no idea which come from algebraic circles. And we know that outside very special case, not all come from algebraic circle. In the extension group you have there. Now, the reason it matters, suppose you have some cohomology class in this Hodge group. So an integral object with some invariance by the circle. Often, so it can be given by a topological circle, that's assumed, and you can cut it, restrict it, cut it with each slice. And the interesting case is when you cut, you get something which is 0. And then, if you knew the more precise class of the circle, if you knew where in this group you are looking for some circle, then you would be able for each section, if you just cut you get 0, but in interesting case, you can predict where you would live in this more refined group if you had an actual algebraic circle. And if for each cut you were able to find the circle, algebraic circle with the correct class in this more precise sense, then you can hope to be able to glue them all together to obtain the circle in higher dimension. But there are a few cases when this works, where you know that all possibilities are satisfied, and then this method proves the algebraic. So the case of cubic fourfolds, for instance, can be reached like that. Yes. But in general, this slashing method, we cannot use it. So that's why it's difficult to prove it. Now, why is it difficult to disprove it? So at first sight, there should be many methods, because there are many ways to construct the cohomology of algebraic variety. I have explained 2 of them integrally with actual circle, topological circle, in terms of the Durham complex. And this can be refined by using differential form, which, if for non-trivial variety where the equations are with rational coefficient, you can obtain some rational vector space instead of those real vector spaces. For some other theory, you can get some Galois action. And for each theory, what comes from algebraic circle has some very special properties. So you would say, let us pick your preferred Hodge circle and let us check if it satisfies the criterion which come from the other cohomology theories. Now, the problem is that I would say there are 2 kinds of algebraic circle one can try to play with. First, there are some obvious ones. For instance, if I have a variety X of dimension D, I can look at 2 cohomology groups which are equidistant from the middle, and I can pass from circle corresponding to 1 to circle corresponding to the other by cutting with hyperplane. And one knows that for Hodge circle, this is an isomorphism. So this gives away from an Hodge circle of small codimension to deduce a circle of Hodge circle of big codimension, and take such a Hodge circle of big codimension. That's a candidate Hodge circle, but because there is a reasonable way to construct it, it will pass all the criterion corresponding to all the cohomology theories. So that's, for obvious circle, you don't make a counterexample like that. And the problem is that, essentially, except very few cases, it's very difficult to construct a Hodge circle except by exhibiting it as an algebraic circle. The problem is as follows. The definition of this action of the circle on the real cohomology, which is used in the definition, is something analytic. And by brute force, you cannot tell if something is fixed by a circle or almost fixed. And in practice, it's not even possible to tell that if you move a little the parameter, it will become exactly fixed. So we have in general no method of exhibiting candidate obstacles. So that's why we are not able to use all those criteria to prove that something is not algebraic. Now, I had promised to say a little about why we care about the conjecture also. So, the beginning of algebraic variety was the theory of elliptic integral and more generally of abelian integrals. And this is all related to the first cohomology group of an algebraic variety. And abelian variety, or those first cohomology group, have a beautiful theory. And one would like very much to have something similar for higher cohomology group. And a first thing one would like to do is to extract from an algebraic variety something which reflects only some higher cohomology group. And the idea of Grothendieck for doing this is to construct some endomorphism of the cohomology using algebraic circles, so that one has a projection to one cohomology group only. So that's the theory of motif, which could be used to many things. If one has a good theory of motif, it tells things about some integral having rationality properties or related to 2 pi I. But essentially, if one had Hodge theory, it would be of big help to have a good theory of motif and to be able to understand better the higher cohomology group of algebraic varieties. And it's early, but that's all I have to say.